The two-sample t-interval is used to estimate a difference in population means mu1 minus mu2. The conditions are pretty simple. You need two independent simple random samples and normal populations. The formula has the same structure as any confidence interval. It consists of an estimate, which is in this case is x1 bar minus x2 bar, plus or minus a critical value from a t-distribution in this case, times a standard error, square root of s1 squared over n1 plus s2 squared over n2. S1 and S2 are the sample standard deviations, as x1 bar and x2 bar are the sample means. N1 and N2 are the sample sizes. For degrees of freedom, when you're trying to find your critical value of T star, the conservative approach is to use the smaller of N1 minus 1 or N2 minus 1. That's going to give you a wider interval in general, but you could also find your degrees of freedom on a calculator or computer, and that'll give you a narrower, more precise interval if you do that. Doing that, calculating the degrees of freedom using the formula that computers and calculators use is pretty horrendous if you try to do it by hand. So if I were doing this procedure, I would use this conservative approach. If I were doing this by hand, if I were doing it on a calculator, I'd let the calculator calculate the degrees of freedom for me. On the calculator, this is at stat test 0 to sample t interval. Let's look at an example of how you could use this. It's a study that was done on taking a calcium supplement and whether it would reduce blood pressure. A randomized double-blind trial assigned healthy black men to either a calcium supplement for 12 weeks or to a placebo. The 21 subjects were divided 10 into the calcium group and 11 into the placebo group. And these are the calcium reductions for every individual in this study. We want to estimate the difference in mean blood pressure reduction for calcium minus placebo with a 90% confidence interval. Now, the procedure for doing a confidence interval, again, is basically you define the parameter that you're trying to estimate and check the conditions, actually construct the interval, and then write a conclusion. So here is the parameter we're trying to estimate, mu1 minus mu2, where mu1 minus mu2 is the difference in mean blood pressure reduction, calcium, group 1, minus placebo, group 2. Conditions are two independent simple random samples. And now we have random assignment to treatment groups in an experiment, so that takes care of that condition. Normal populations. Well, we don't know that the populations are normally distributed. We can't rely on the central limit theorem because we have very small samples here. So what we have to do is look at the data and see if the data are at least consistent with normal populations. In this case, the data for both groups contain no outliers, and they're fairly well behaved. Here is a stem plot of the blood pressure reductions for group 1 and group 2. And you can see that the blood pressure reductions, some of them were negative. That means that blood pressure actually went up. And most of the blood pressure reductions for the calcium group are positive. Most of the blood pressure reductions for the placebo group are actually negative. And this is the key down here that shows what's going on. Now, the placebo group has a very nice bell-shaped, symmetric, single-peaked distribution of values. And there are no outliers in this distribution, so that's ideal. On the calcium side, it's a little bit skewed. It's not ideal, but there are no outliers. And in a group this small, only 10 observations, you're frequently going to see stem plots like that where things aren't quite as well behaved as you would like them to be, but that's a function of the small group size. And if we had larger groups, perhaps this would fill out in a more normal manner. But it's not inconsistent with the normal population. You could certainly get a distribution of data like that from a normal population. So we're going to go ahead and do this procedure. Now, in group 1, we have 10 subjects. The mean blood pressure reduction was 5.000 with a standard deviation of 8.743. In group 2, we had 11 subjects. The mean blood pressure reduction was negative 0.273 with with a standard deviation of 5.901. Now, when constructing the interval, if you're doing it by hand, write the formula, show your plugins, and get your interval. So here it is. It's a 90% confidence interval for mu1 minus mu2. And again, here's your formula. Write that out, show your plugins, and then simplify it down. The interval that you get here is negative 0.754 to 11.300. That is based on 9 degrees of freedom, using the conservative approach where we take the smaller of n1 minus 1 or n2 minus 1. In this case, n1 is smaller. It's 10. 10 minus 1 is 9. So we use 9 degrees of freedom, and that's where we got this 1.833 critical value from Table C, the t-distribution table. We started in the 90% confidence column. We went across the 9 degrees of freedom row, and this is the value where that column and that row intersect. If you do this on the calculator will use a much more complicated formula and will calculate degrees of freedom to be 15.59, and the interval in this case on the calculator is negative 0.4767 to 11.022. Now you see that the calculator's interval is narrower than the one we got by hand. That's because the calculator is using a higher number of degrees of freedom, and so the value of t star that they would use would be smaller than this. The margin of error would be smaller, and therefore the interval would be narrower. Either way, we have a confidence interval, and when you write a confidence interval, you should always say what it means. In this case, I am 90% confident that the true difference in mean blood pressure reduction, calcium minus placebo, is contained in the interval from negative 0.754 millimeters of mercury to 11.300 millimeters of mercury.